Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today we're going to talk about precise thread-modular verification. It's a joint work with my supervisor Andreas, Podelski, and with my former colleague Andrey Rybalchenko, who is now at MPI in Germany. So we are from Freiburg, Germany. So when you try to verify concurrent programs, you always run into state space explosion, into state explosion. It's the curse of concurrency. So the current research in model checking was biased towards one direction, namely to try to optimize the exponential time approaches and to create faster versions of them. So there are exponential cost algorithms, and we try to make them faster. Now let's try to exhibit an alternative approach, which is to start with a polynomial cost algorithm, which is incomplete, and to make it more precise. So we would like to add some fine-tuning to a polynomial cost algorithm, and eventually to make this fine-tuning automatic. So the approach that we have taken is the approach of thread-modular verification, which was initiated by a paper of Shaz and Flanagan. And this approach works roughly as follows. When we do our search for successors of states, so we start with initial states and compute the successors, we don't compute successors of the states of the whole program, so we don't generate states of successors of states of the whole program, but we generate successors locally. So for each thread, we generate successors only with respect to this thread. So we don't store tuples which describe the configuration of the whole program, where the first thread is, where the second thread is, where the third thread is, but only we store, we accumulate the states of each thread locally. So we have a set of states where the first thread can be, a set of states where the second thread can be, and another set of states where the third thread can be, and we let these sets grow during the search. This is the idea. This method is very fast. It is polynomial in the number of threads, and it is sometimes incomplete. So you cannot prove with this method everything. It has polynomial time. It has polynomial runtime. And so for some examples that we're going to see right now, this method is incomplete. So a typical example that our approach is going to run on is presented here. So you don't have, so it is very, very simple example. You don't have to understand much more. There are two threads, and they try to acquire a lock, go into the critical section, and after quitting the critical section, they release the lock variable. And if the lock variable can take only values true or false, that means lock is acquired, lock is held, or lock is not held, then this program cannot be handled by the thread-modular approach. And if the value lock has more values, namely lock is not held, or lock is held by the thread number 1, or lock is held by the thread number 2, then this program can be tackled, so the correctness of this program can be proven by the thread-modular approach. So the correctness would be that there is no run, which starts in the initial state, and whose final state is a state where the first thread is at location L2 and the second is at location M2. And we ask ourselves, where does the incompleteness come from? And the answer is hidden in our paper of the year 2006. So I'm going to explain right now what is the connection between thread-modular approach and so how to describe the incompleteness in the modular approach. So our result is that thread-modularity, or the analysis of the thread-modular approach, can be explained in terms of abstraction. So you can view the thread-modular verification algorithm as a kind of independent attribute analysis, where the attributes are the states of the first, second, and so on threads. So you can also formulate this approach in the Cursor style, and this is what I'm going to. This is what will be the main idea throughout the remainder of the talk. So in the Cursor style, you can have different abstractions, different color connections, and the one we're going to use here is the Cartesian abstraction. So the whole thing, the whole thread-modular approach can be explained as simply abstract interpretation with Cartesian abstraction. So what is Cartesian abstraction? It's simply if you have a set of tuples, then you over-approximate this set of tuples by the smallest Cartesian product, which includes the set of tuples. That's all. So this is the basic idea behind the thread-modular approach. So if you don't know what thread-modular approach is, you can simply think of this and then you know it. So how does the abstract interpretation, so how does the abstract fixed point computation works in case of Cartesian abstraction? So we can make an illustration of, a simple illustration of this. We start with the initial states, or approximate them by the smallest Cartesian product, which contains the initial states. Then compute the successors of this or approximation, add to what we have before. So this square means denotes the set of states which was obtained at the end of step number 1. Take the union and over-approximate this union by the smallest Cartesian product, which includes both, and continue this way. So take successors, add to what we had before, over-approximate, and so on. And due to incompleteness, we might hit the bad states, so the error states which are given by the user. So this might happen due to incompleteness, or this might happen due to the program being incorrect. So what do we ask right now? How to be a bit more precise? Is it possible to be a bit more precise in the setting of Cartesian abstraction? And if yes, how? So the first question that we're going to ask is whether we can fine-tune a Cartesian abstraction in order to obtain a more precise answer, in order to so that for each step the or approximation is not so coarse. And even if we can fine-tune the thread-modular verification, can we still have polynomial time complexity? So remember, the pure Cartesian approach has polynomial time complexity. There is an algorithm for it, presented by Shas. And the question is, when we fine-tune Cartesian abstraction, can we still be polynomial? So let's present a simple fine-tuning approach. We call it fine-tuning via exceptions. We're going to propose a new abstraction in very simple 3 steps. The first step is to take a set of states, to separate it in 2 parts, remove one part, apply the Cartesian abstraction to another part, and then add the first part back again. So thus you apply the Cartesian abstraction not to the whole thing, but only to a part, which leads to a bit more precision. So this can be visualized by the following picture. You start with a set of states, separate it into 2 parts. So in this case, they are approximately equal from the array, but in general they can be, E is 1 point and here is the rest. Then you over-approximate one part by the Cartesian product, so the upper part. And then the resulting over-approximation, the resulting step is, the result of the whole operation is the over-approximation together with the set of exceptions. So we call the set that we remove and then add back again the set of exceptions, the exception set. So no state explosion happens with this approach. There is some non-trivial combinatorics going downstairs, so that you can actually prove that if you take a very good representation of E, then no state explosion occurs. That means you are still polynomial in the number of threads and in the size.
That cannot be true for an arbitrary exception set, because if my exception set is the entire set at each step, right, then you'll get vanilla state space exploration, right?
Then you are done in one step. But then this set is represented, of course, in such a way that it contains exponentially many states. So you cannot push exponentially many states into a polynomial size structure. So the approach is polynomial in the number of states and in the size of representation of the exception set. So if you have everything inside the exception set, then of course you are done in one step.
No, why will you be done? Oh, because you will add the entire exception set.
The entire set of states. You're done in one step, so.
So you have a theorem which says that no matter what exception set I use, this computation is polynomial.
In its size and in the number of threads, yes.
Okay.
But E is part of the input of the algorithm. So the size of E
is, I see,
is a parameter.
But is this the size of E is in the explicit representation of E? Like enumeration of the number of states? Enumeration of the states? Or how do you represent E?
We have two different representations. So if you can take, of course, this one as simply as a list of tuples, and you have one algorithm for this list of tuples, and then we have a polynomial time bound in the size of this list. You have also another representation as the list of Cartesian products, as a set of Cartesian products, as a list of Cartesian products, which allows you to store
more states.
Exponentially many states in a polynomial size structure. So assuming that the number of Cartesian products is small.
You still have polynomial complexity.
Yes.
Why are they called exception states? Is that related to programming exceptions, or?
No, so it's not related to Java. You can also, I have seen only once on the web some mathematicians using the term exclusion sets, but it's not in the context of program analysis. So there are other names by other people who say Qadeer sets. So some of you may hear Qadeer sets.
So the set remains fixed throughout the whole step computation?
I'm going to come to this later. So for this simple until this slide, think that it does remain constant throughout the computation for this moment. So we have our great theorem, which says that if you apply this exception state approach, then the time needed to compute is polynomial number of threads and size. In the number of threads and in the size of the representation of the exception set.
Maybe exponentially. Now your representation may be linear in that number of states, but the number of states is exponential.
We have the representation which is so as I have just explained to Shah. So the number of the size of the data structure is of course a parameter, right? So we have two different representations, and one representation is the trivial one. I don't understand you. What do you say?
Well, you're saying it's polynomial in the size of the program?
Well, I guess
In the input size.
I'm waiting for
No, but maybe the answer is just it's polynomial in the size of the program and the size of the representation of the exception set.
But the size of the representation of the exception set is itself non-polynomial in the size of the program.
In general, yes. In practice, we do have for very many programs the fact that the size of the exception set is small.
There's no thread explosion in the first place, if that's the case.
So you can, you should pay attention. So if you would like to combat against p-space explosion, then of course you are done, because you cannot await polynomial time proofs for the p-space complete program, for the p-space complete problems.
That the size of the program, you're not thinking about variables as a program size. You are talking about all the values of the variables. So you're taking that p-space out of the picture. You're talking about You see,
Yes.
you see what I mean?
But that's what I suspect. But then, I mean, of course, I mean, a simple traversal of the state space, exponentially large or infinite state space, I mean, it's linear in the size of the state space. There's no problem.
but
So
That's the fine print here that we are trying to clarify. But maybe I should let you.
No, but let me find out how they choose the exception set. How do they choose that set so they control the size of the exception set?
that's right.
But according to Shah's question, etc., it could have been perhaps anything. That's this parameter. But go ahead, sorry.
But perhaps this is my fault because I forced Alexander to be informed in this talk. So maybe I can help. So it's first of all, so it's the exception set is what the user gives to the algorithm. So he gives the program and the exception set, some representation.
And you assume it's polynomial.
No.
We don't care.
The exception set, you have some representation which is part of the. I mean, the representation is part of the input. The input is the representation of the exception set and the representation of the program. Right? So we say that the representation of the program is the size, is the number of threads. Now the representation of E, you cannot say it's polynomial or exponential input. It's just part of the input, right?
Okay.
And if the exception set is empty, then the size is 0, then you have the old thing.
Okay.
So this is the main question. How about the practice? So whether we still have a practical evidence for our approach, and the answer is here. So we have done experiments for some programs, and here is one example for a class of programs where it works. So we have n threads, and each thread consists of m critical sections. So critical sections in the sense statements of the form acquire lock, do something, and release the lock variable. And we have run our algorithm on this program and run the straightforward search on this program. So you have two parameters to choose, the number of threads and the number of states, and the number of critical sections. So if you have 17, if you have 17 threads and run the straightforward search, then you don't terminate within the 2 hours bound. So you time out very easily, and you see that this curve is exponential, displays exponential behavior. And on the other hand side, if you apply the exception set approach, then you can handle 100 threads and up to 9 critical sections per thread. So of course, yes. So of course, this is not. We have to give a set. This is not for free. We have to give the exception set for this program. So I'm not. So actually, I'm not going to show it right now. But it has a very simple structure. So it is comprised of n Cartesian products which are user given. So the exception set for this program is of size which is linear in n, which is linear in the number of threads.
You could write it on the.
Yes, I could write it. So the exception set for this program is, so first the exception sets should contain states of the whole program. So what is the state of the whole program? It's evaluation of a shared variable, lock. There is only one shared variable, comma, the value of the program count of the first thread, comma, the value of the program count of the second thread, comma, and so on. So the shared part should be true. That means the evaluation of the single variable lock, which is 1. And the other, and the local parts look as follows. So we choose the representation of the exception set as a union of Cartesian products. So the first Cartesian product looks as follows. The first thread is in the critical section. I write it like this. And all the other sets, all the other threads are not in the critical sections. I write it like this. union something else. Something else is the first thread is not in its critical section. The second thread is in its critical section. And all the others are not in their critical sections. And so on. So the last Cartesian product is the first thread is not in its critical section. The second thread is not in its critical section. The n minus first thread is not in its critical section. And the last thread is in its critical section.
What is that true X there? True star? What is that?
Cross. So a single tuple from here has true as...
Oh, that's the shared part.
Yes, the shared part. Has true as the relation of the shared variable block. This set is user given for the moment. And now the question is whether it is possible to find it automatically. So how would the approach, how would we proceed? First, we start the same iteration as before with the empty exception set. So we start with the initial states, over-approximate them by a Cartesian product, take the successors, add to what we had before, take the union, over-approximate, compute the successors, add to what we had before, add to the set of states, to the over-approximation of the set of states after the second step, take the union and over-approximate it, and so on, until we hit the user-given bad states. Then we look at the intersection of the bad states with the successors of the over-approximation at stage 4. So we look at the intersection of the blue circle with the red cloud, and take the predecessors of this guy, and so the blue circle is the set of successors of the over-approximation at step 4. No, after. So.
No, but not in step 5. Yeah.
Okay. Yes. So you take the predecessors of this intersection. This is the red cloud for step 4, and then let's assume that there is still an intersection of these predecessors with the blue circle for step 4. We take the predecessors once again.
Sorry, I have a question. So in computing that blue set in itself might be exponential.
Theoretically,
The reason that it's polynomial is because you can compute the next step on the whole abstraction of a set of states. If you have to take the set of states, take each one, and make its next step. Well, there may be potentially many of those, so you can't really compute precisely, right? So what do you mean by this?
so actually you can compute the blue set in polynomial time. It has a simple reason, namely a transition relation of a multi-threaded program has polynomially many transitions in the size of the program. For each of these polynomially many transitions, you do the following. You apply this single transition to the whole Cartesian product. And then you can show that you generate only polynomially many Cartesian products. So the blue circle has actually a polynomial size representation in the number of threads. So for this step, we see that the predecessors, so the red cloud, does no more intersect the blue successors and does no more intersect the over-approximation of set of states at the second step. So does no more intersect the square and does no more intersect the blue circle. So for this step, we introduce our first exception set and do it as follows. So we have this picture at step number 3. So what do we do is trying to compute a maximal subset of B, of the blue circle, whose projection on the second component is equal to the intersection of projections of B on the second component and of F on the second component. So you can visualize it like this. You look what second components do B and F have in common, and then take the maximal.
Here you're assuming that there are 2 threads? That way you're talking
Yes, so for simplicity, assume that we have 2 threads. Yes. And then you take the maximal subset of B, whose second component lies in the intersection of second components of B and F. So in general, you don't have to take, of course, exactly this E, but you can take any superset, which is still inside B. And you can compute it, the set E, in well, you can compute exactly this set E in polynomial time, yes. So what is done later is trivial. So you subtract E from B, take the O approximation of B with what we had before, and add E back. And you see that the new representation, E together with the old set of, with the old over approximation, does not intersect the bad states F. You have chosen it like this.
Why did you choose 2? Why not 1?
2 what?
That why is there 5 2? There are 2 threads, right? 1 and 2.
Yes. So in general, you can choose 1 or 2, and you try what works. So you can also choose 1. Then you have to exclude this part. So we have chosen always to take a subset of B as an exception set. There are special cases, yes, where you can neither 1 works nor 2 works. Then you have to do something else. But for this simple picture, so there are several cases which you have to consider. For this simple picture, we take the projection of the second component. So there is a case split, and this is one case which occurs relatively often. So note that you cannot take the Cartesian abstraction of the exception set instead of the exception set. So if you take the Cartesian abstraction, the Cartesian hull of E, then you might intersect the F here. So you really have to take the exact E.
So the reason that E can be represented in polynomial spaces because it comes
from B.
Step before, which was Cartesian abstraction. That's in general, this is not the and you don't carry it around after that. What happens next is E.
I'm going to show this right now. So this is the next round. The first 2 steps are as before. In the third step, before applying O approximation, you take E back. You take E out, and then apply the O approximation, and then you add E back. And then you propagate the E, so that T is also the exception sets for all further steps, for step number 4, 5, and whatsoever. So you compute the successors of the E end of the Cartesian product, add to what you had to the Cartesian product you had before, subtract the exception set, or approximate it, add the exception set back. So in this special case, adding the exception set back does not change the set of states. So for this picture, it is inside, but in general, of course, E might be still somewhere outside, right? So in the next step, the same thing happens. You subtract E or approximate it, add E back. And if you don't hit the bad states, you're happy. One can show that the set of bad states no more intersects the blue circle. This is a proof. So there is some proof which shows it. The only bad thing that could happen is that the set of bad states intersects the O approximation, but does not intersect the blue circle and does not intersect the square. So the only thing could happen that the bad states intersect somewhere here, so that they have an intersection here. Then you then you discover a new exception set for this picture and add it to the exception set that you already had here.
Wait, but if you know that the bad is never going to intersect with the blue, why don't you stop? I mean, when you know there's no error. So that can't be, you know.
So in general, so there is of course there is a slight possibility to to optimize at this step, right? So to check whether the bed intersects the blue and the square. There is a slight optimization possibility, but in general you also have step 6, and
You're saying only up until the state to the step where you had run it before. You're saying, is that true?
so the bed does not intersect everything here. Does not intersect 1 to 4, right?
But it might in step 6.
It might do it in step 6. So if bed intersects something here in step 5, then it does definitely intersect something in step 6.
No, but also, I think the Utan's question was, it does intersect in step 5, but this is not yet the fixed point. It was just where he did the refinement.
I thought the claim was forever there.
No.
Okay. So what prevents the step E to double, for instance? So like in step 3 we added E and then carried over to step 5, and 5 we need to do the computation again because to check whether we have a bad state or not. Now we compute a new set E and we add it to the previous one. What prevents this new set E to be the same size as the previous one?
The same size.
Yes.
It can be the same
But
size.
then it's exponential because then you double whenever you do this process.
So-
it grows exponentially.
So in worst case, of course, you have an exponential thing, so it is unavoidable. The question is how good. No. The question is
One iteration is polynomial. Sorry? Any one iteration is polynomial.
Yes, okay,
Right, but
of course,
that's
you double
not-
and close the size. Okay, yeah, okay.
no. As soon as you fix the E, if E remain constant throughout, then we terminate in polynomial in many steps.
Okay.
So assuming that you hit no bad states and you don't stop iteration once again. So that's all. I'm going to come to the related work. It consists of the paper of Shaz and Cormac, Flanagan, about Thread-Modular Verification from the Spin Workshop of 2003. So the paper actually presented a Thread-Module method. Another direction is explored by Roman Manevich and Mulis Agiv. So they do kind of Cartesian abstraction for analysis of programs which operate with heap, and they propose some kind of refinement there. So they are able to handle heaps and concurrency, but the abstraction is user-tuned. And Kedran Yoshi and Ariel Cohen explore what happens if you try to move information from the local part into the global part and make their analysis more precise by exposing local states of one thread to other threads. So of course there is a lot of other work on compositional reasoning, which I'm not going to mention, and I don't know all the work on compositional reasoning, so there is tons of work on this subject. So let me thank you for your attention, and if you have questions, I'll be glad to answer them.
Any more questions?
So what's the intuition for how to choose exception sets? I mean, if you look at the one example you gave, it seems to be sort of it's a safe set. It's part of your safe state setting.
Mm-hmm.
Is that, have you got enough experience to know anything about how to choose exception sets?
So in general, it is the following. You have to examine your fixed point computation with Cartesian abstractions, and you have to look at it. And then you can try to extract exception sets. What you can also do is to choose. So in theory, you can choose any reachable set as an exception set, and then there is a theorem which tells you that you are more precise. So if you choose any reachable set of states as the exception set, you can get more precision. You don't get less precise.
But I think what Manuel is asking for is that if you look at that program, the example program where you had the nice graph, in that program, locks are being used. Okay, a programmer who uses locks doesn't know anything about exception sets and doesn't know anything about all this Thread-Modular stuff.
Mhm.
He's thinking that I'm using locks to have critical sections, and he might be willing to annotate this program with saying, okay, this data or this critical section is protected by this block. Is there
So-
some connection between that programmer level intuition and exception set?
So for a programmer, actually, we can say that if you are a programmer and you would like to devise an exception set without having deep insight into the Cartesian products, right?
Yes.
Then we can tell him, okay, devise, put some annotations which would generate the exception set like this.
But what are those annotations?
So we'd simply tell him write this set down. All right, so
He doesn't know about Cartesian products.
he doesn't know about this.
Cartesian product.
So of course you have to have some language which allows you to write such kind of stuff down.
One thing that might be useful, one thing that might be useful is to try to figure out the exception set for programs that use some synchronization that is not mutex related. Then we can try to see what the commonality is. Right? Maybe it uses events, right? Maybe it uses. Also, the other thing is that what if that particular program, every mutex was the same mutex? What if there were lots of different mutexes used, right? Which is what
Yes.
is more common, right?
Yes. So it is actually difficult for a programmer to devise an exception set in case of several mutexes. In case of presence of several mutexes. But I have devised it, yes. The astonishing fact is that you still only need a sub-exponential size exception set. So there is an exception set which doesn't have an exponential size and still allows you to check it. Right.
I see. Okay.
So, but it is, as you said, a programmer does not. So I can tell the programmer, write this set down, give this set to a model checker in some annotation language. But he wouldn't know why would I give it to him. He would be able to use it.
So I was going to brainstorm about what that means. I think what this exception set expresses is the mutual exclusion that the log provides. And I guess the thing that the Cartesian product can't handle is state that is, if state in one thread excludes a particular state in another thread, but not in all executions. So in other executions, you could have that state in the other thread and not in that one. So anything where state in different threads excludes each other would lead you to have to create such exception sets.
That you would like to prevent creating connections between states of different threads. So you would like to prevent creating of certain tuples. And then you put, so a certain tuple is created during no approximation if you have two tuples which contain the components. And then the components come together by the Cartesian abstraction. So we have a point here and the point here, and the Cartesian abstraction inserts this one. Do you see it?
Yeah.
And then you put let's say this one into the exception set, or this one, so it's arbitrary.
We understand Cartesian abstraction, but we're trying to be more concrete, right? We're trying to apply to
Trying
some
to
insight,
yeah.
right?
Like if you take a real program, real Cartesian abstraction remotely work or not?
Remote liver?
If I have a program where, in the very beginning of the program, one of my threads grabs some resources and then releases it for the rest of the execution. Then Cartesian abstraction, I don't think will work very well because
Cartesian abstraction is like you don't care, right? In your local state, you don't care where the rest of the exact state of.
So your question is how to choose the exception set if you would like to prove that a thread always releases the resource that it has grabbed.
I think I'm trying to get a hold on an understanding of what's the kind of program where Cartesian abstraction will work versus the kind of program where it won't work. Or
Just for Cartesian abstraction.
yes,
Not even for exception.
yes. So it's related to this because if the Cartesian abstraction doesn't work well to begin with, then this exception set can probably help it in some cases, but maybe not in others.
So
There are correlations between locks. They have to be the exception sets. Like there are two sets of locks, for instance, that are not
subtracting in a way. I mean, they are protecting different variables. Then you can basically blur the state of a set of blocks with respect to the other set. And so that's what Cartesian abstraction, right? But here, actually, I don't know if you have this hierarchy, you can vary all the time, so to speak, because you carry these exception sets all right. I mean, so it's like once you've decided to keep track of the correlation between some variable, that's it for good, forever.
Forever on the right. But of course, if you have to devise the exception set on the left, then you have to forget everything on the right.
So one thing you didn't talk about at all, which is, I mean, if I remember correctly from Strauss's original work, you had to have a sort of assumed guarantee reason. You have to have a formula that describes what the other threads were doing, and you have to apply this at each step to,
You are right. So
mutate the global shared state, right? I didn't see how this comes into this whole description.
So the initial description of the Thread-Modular algorithm was in the assumed guarantee style. So they were guarantees of how other threads behave. The guarantees were expressed, let's say, for simplicity, as formula over shared variables. And then you try at the same time to infer these guarantees online and to model check each thread using the guarantees of all other threads, simply by inserting between each two statements all possible actions of global variables that are in the guarantees, that are represented by the guarantees of the other threads. So this was the style of thread modular analysis by Shaz, and I haven't talked about this style here. You're right.
But what I'm saying is, if you analyze this example that you gave, right? I mean, you have to assume something about the shared variable lock, right? So do you just assume it gets mutated between each step as well?
Mm.
Or what do you do? I mean, I just don't understand the practical setup of how you do your analysis or your state exploration.
So there are two ways of viewing it. My view is Cartesian view. Your view and your view are views. I assume guarantee views. So
Cartesian view, but the problem is in the Cartesian view, right? Each part of the Cartesian product is the thread local state, right?
Mhm.
Well, it doesn't contain the shared variable.
I see.
I don't see where it is.
So for the presentation, assume that there are no shared variables. So pretend that there are no shared variables. We have a theorem which states how this works for shared variables, and you have to imagine the abstract domain not containing of Cartesian products, but not containing Cartesian products, but containing maps from shared states to Cartesian products. So for each shared state, so for each relation of shared variables, we have a single Cartesian product, and during the forward abstract exponent computation, you enlarge these Cartesian products.
Then you become exponential in the state of the shared state.
Yes.
So you're exponential in the size of shared state. So I don't struggle against the explosion problem in the number of variables.
You're not exponential in the size of the shared state. You are still polynomial in the size of the shared state. You're
In the
exponential
size of the variables.
global variables.
Right.
Yes, that's what I meant. Size of the shared state meaning the whole state. Whatever you can express. If you have 32 bits, then you have 2 to 32 states.
Yes,
Right?
but
Yes.
I mean, that is a problem even with the local states, right? Because supposing you have a
Yes.
local variable,
Yes.
you have n local variables.
That's the problem.
So the only problem he is solving is the exponential in the number of